So today it's a great honor to have Alex Stoll here. I assume that all of you know Alex, one of the nicest PhD students that we had. Very elegant in his look, as you can see. So Alex did his undergrad here, then he continued his PhD and worked with Bram and Alison. He did various of stuff. Probably a lot of you use his boron diffusion recipes. He did aluminum oxide passivated contact and IBC solar cells as well. So he submitted his thesis just a few weeks ago, and I pushed a bit and asked him to have his presentation. I must say that Alex was quite happy also to share his knowledge here. So please welcome Alex, and well done for your thesis.
Thank you, Ziv. So thank you, Ziv, for the very kind introduction. And yeah, it's a real honor to present here in front of my colleagues and also to see some of the contributing faces that helped out with this work. So today I'll be talking primarily about my PhD thesis work. Bram was my supervisor, Alison was my co-supervisor, and we looked at how to improve the carrier selectivity of diffused silicon wafer solar cells. So I wanted to sort of frame this talk by really going back to a very simple look at how solar cells work, to introduce sort of carrier selectivity again. And so there's really two fundamental things that solar cells do. One is obviously convert photons into carrier pairs. And the second is about the separation of those pairs and extraction to contacts. And that second function is really related to carrier selectivity. And so there's two sort of functions there. We engineer carrier selectivity to reduce recombination, to keep those whole pairs alive as they move to their respective contacts. And secondly, we do it to facilitate the extraction of charge carriers. And so typically this is done via doping, but also there are some advanced concepts like band gap engineering, which also people look at. But so having talked about carrier selectivity, I want to highlight sort of two trends. And the first is that the J0 has to come down in industrial cells if we are to see continued improvement in device performance. And secondly, if you look at what sort of metallization technologies, you can see that screen printing is going to stay there for a while as plating takes up a larger portion, although I think it's also worth mentioning that they tend to keep revising that portion down, but nonetheless it's still there. And so really we wanted to focus more on, well, for the current existing diffused homojunction solar cells with their current J0 values and with the pipeline of metallization technologies that they have coming, how can we improve these devices? So that was the aim of the thesis. So in today's talk, we're going to cover quite a broad range of different approaches. I'm going to start firstly by looking at majority carrier conductivity on heavily diffused P+ and N-type surfaces. So typically how we can exploit very specifically this production anomaly when we make PERC cells to improve the N+ contact. Secondly, I'm going to look at how we can make nickel-plated contacts to boron diffused emitters. And then we're going to look at the carrier selectivity at non-contacted surfaces. So what happens and how can we understand the surface recombination of diffused and inverted surfaces? And how can we take this understanding and apply it to characterize these surfaces and interfaces better? And then as the final part of my thesis, we tried to tie this all together with homojunction IBC solar cells, specifically looking at some integrating these results and how we can improve these diffused IBC cells. So let's start with the first one, this unintentional effect that happens when you make PERC solar cells. So what am I talking about? So essentially, when you make a PERC solar cell, in some fabrication sequences, you do the front side nitride and then you do the rear allox and the rear nitride stack. And particularly when this is done, for instance, in PECVD in a tool which has both an upper and a lower source, you can get some wraparound of aluminium oxide onto the front side. And similarly with ALD depositions, it's actually very difficult in practicality to get a truly single-sided deposition. So manufacturers were reporting that aluminium oxide was wrapping around onto the edge of the wafers. So the question really was like, well, what's the effect of this, this wraparound? What happens when the ALOX gets on top of the ARC prior to firing and people try and make contact through that? So typically we were looking to answer, what is the effect? Can we model this? And can we replicate this with actual solar cell devices? So the first thing we tested was just to fabricate some very simple TLM structures. We took industrial precursor wafers from an industry partner. So here we are. We had some ALBSF/PERC precursors, and we also took some PERT samples because that's what they're interested in, which were differentiated by they had a thin silicon oxide layer, and that was because they were actually ion implanted. We then screen printed them with one of two types of paste, and then did a firing optimization at different temperatures and then various speeds for the PERT cells, and then laser cleave them to do the TLM measurement. This is the typical schematic. Those of you who've worked up in 2, 3, 4 know the tool that we use to probe the fingers. It's an equidistant linear TLM structure, and there's equivalent sort of resistance network where you probe across interjacent fingers. And I'll talk more about the error involved and exactly how you get the measurement out, but for now just bear with me, that's what we did. So this is sort of the first result of the firing split for the PERC type structures. So you've got the temperature along here. You can see the breakdown for each thickness. That's in nanometers of aluminium oxide on top of the silicon nitride. And you can see that there's a characteristic U-shape, right? Which is sort of what you expect as you go between underfiring, overfiring, and the sweet spot in the middle. What's interesting here is that actually the 3 and 5 nanometers, so the yellow and the green, on average perform better than actually the uncapped case. So there's a situation where having a small amount of aluminium oxide was actually improving your ability to make contact. This was not, however, the case for the 10 nanometer thicknesses, which is typically what's applied in industry. Another curious thing is that the optimal peak firing temperature seemed to be lower than that relative to the control case. So it seemed not only could you get better contact, but you could form it at lower temperature. So this was kind of really interesting. However, it wasn't replicated for the PERT structures, and we think that's because of the intervening silicon dioxide layer. So something's happening with the paste chemistry and the firing reactions there. But, and that was true for both Heraeus paste and DuPont paste. Taking these results, though, we thought, well, maybe it's just not, firing properly. It needs a bit more time or something. So we did different speeds here. So again, the same sort of plot, different temperatures, different pastes. However, we weren't really able to improve relative to the base cases. One interesting point, though, is that if you look over here for just changing the paste can have 2 order of magnitude difference on the contact resistivity. So that's useful to know, at least for manufacturers, when you're trying to minimize this effect if you can't eradicate it. Just simply changing your paste formulation can actually reduce a lot the effect that this can have. So having now got these results, I just want to talk a little about this method because I think it's relevant to people, particularly at SPREE, who use this tool. Now, I think I put this here to just recap. Like when you do the TLM measurement, you're essentially probing the resistance over a varying distance, and you plot that, and there's a linear slope. Now, the simplified sort of equation, if you've got certain ideal case, is this one down here. But in the case that you're doing what we did with interjacent fingers, there's this additional term, which is essentially this resistance network. And so basically, you can't neglect that in certain situations. So there's a few scenarios I want to go through. The first is that you can imagine the current's just going along here and it goes along the path of least resistance, right? So if you've got low contact resistance, it'll actually go through here rather than going underneath the metal. So in that sense, you can assume like a really extreme case, you've got really low contact resistance. This is your equivalent resistance network. This delta REQ is essentially some multiple of your contact resistance. So you can sort of get an idea, is that going to affect your linear slope by comparing, particular values of contact resistance relative to the R total value that you actually probe. And essentially what you find is that if you have a very good contact and your contact resistance is low, essentially this term here drops out and you're essentially negligible addition to that linear fitting because it's not really adding much to those points along the curve. Second scenario is the opposite. You've got a really bad contact and actually nothing flows into the metal and rather it all flows in the emitter. And in that case, it's a multiple of your sheet resistance underneath your metal. And so we simulated here just different sheet resistances, and so obviously the component of the error gets larger as you have higher resistivity in that sheet underneath the metal contact. And the most likely scenario, though, however, is that there's some combination, that it's not all going through the emitter and it's not all going through the metal, but rather there's some gradiated flow which is related to the transfer length into the contact. And so in that case, you have some sort of split here between which one is actually dominating. And so the takeaway from all of this is that if you have a good contact, this method is more accurate, or has less inherent error, I should say, because this term here doesn't contribute as much. On the other hand, if your contact is quite poor, this is actually affecting your assumption that you can linear fit and extract your contact resistance, etc., from the slope method. So essentially, the takeaway from all of this is like the low values that we measured are less inherently inaccurate than the higher values. And so that's just the sort of point that we sort of realized when we were going through the analysis. So having looked at that, we thought, well, what's the effect going to be on a cell, and how can we model like different extents of variation? And so Gridler was a really good tool for this, because essentially you can impose spatial maps of non-uniformity onto a cell and then simulate that effect. So what we did was we developed a model for a state-of-the-art PERC cell. We just took values from the literature and we spat out the numbers, and it looks similar to what industry was reporting. So it's like, okay, great, we got a PERC cell model now in Gridler. And then this is the interface where you can then put in an arbitrary image of non-uniformity. So this is, for instance, a region which we put of 10 millimeters of wraparound from the edge. So essentially what we're saying is that this region has contact resistivity of blah, and this region has the unaffected contact resistivity. And instead of it actually being blah, it was the average values that we extracted from the previous experiments for 0, 3, 5, and 10 nanometers respectively. So we ran that in the simulation, and this is one of the results that you get. This is a simulated PL image with current extraction, and you can see the higher series resistance image appears on the right, where we have imposed that non-uniformity. The image on the left is simply no wraparound to show you what you would expect otherwise. And so simulating the efficiency and the fill factor, what we found was essentially a 3 and 5 nanometer ALOX for this particular cell didn't actually improve the performance, essentially because this was not a series resistance limited cell, or at least not a contact resistivity limited cell. On the other hand, we showed that a 10 nanometer ALOX thickness can have quite a detrimental effect as that wraparound extent from the edge increases. So that was kind of interesting to see. And now we thought, well, can we verify this with cell results? So we then decided to fabricate some standard screen print solar cells, but taking what we learned from the previous experiment, or the simulation, sorry, we decided to significantly reduce the surface concentration to try and force that series resistance limit and to show up in the results. So we fabricated these solar cells. We did light and dark IV, SUNS VOC, extracted the series resistance according to this formula. And then we also did 2 different pace, and we varied the firing temperature for the optimum. So these temperatures correspond to the optimum firing temperature for the 0, 3, and 5 nanometer thicknesses, respectively, from the previous experiments. So this is the cell results. So there's a lot of sort of graphs here, but what I'm trying to point out is that if you look at the efficiency, there's a few key trends. What's interesting is that the 3 nanometer here performed much better than the uncapped case. almost a 4% relative increase. So that's really showing the effect that this can have in the case that your series resistance limited, but also hints that perhaps you can drop the surface concentration a bit with these cells and try and get decent performance. Unfortunately, the 5 nanometer cells didn't perform as well as the uncapped case or even as well as the 3 nanometer case. And there's a lot of spread in this data, so I think that's probably related to some non-uniformities in the deposition or something. Now, in terms of trying to analyze and prove that this was related actually to the series resistance, we had to do a little bit more analysis. So just did some basic correlations. So we found that efficiency correlated very well with fill factor, not so much with VOC and JOC. And similarly, efficiency trends very well with series resistance and not so much shunt, J01, J02. So for us, this was like assurance that actually we're testing the thing that we want to test, and the signal and trends that we see in efficiency actually correlate to the thing that we were trying to change. So that was pretty much that work. And what we showed was that the thickness of AlLOX wraparound has a significant effect of contact resistance during firing. Particularly, 3 and 5 nanometer thick AlLOX layers were shown to reduce contact resistivity in the TLM structures themselves. 7 and 10 nanometer layers were shown to increase, so that's quite detrimental. Importantly, the paste composition and manufacture can significantly affect your contact resistivity during firing, and varying the speed was not able to improve the contact resistivity. Now, we showed that Gridler can be used to effectively simulate this, and when we fabricated solar cells, we found the trends were consistent with the 3 nanometer layers, but not with the 5 and 7 and 10 nanometer layers. So that sort of wraps up that chunk. I want to now move on to nickel-plated contacts to boron diffused P+ silicon. And first, just sort of ask the question why we're even interested in this in the first place. So, as I pointed out, there's a growing, although small, market share of N-type solar cells which require contact to a P+ emitter. There's the broader benefits of plating, so the self-aligned, potentially low cost, high aspect ratio. There's no problems with AL spiking, particular for P+ screen printing on P+. There's potentially processing advantages of plating both N-type and P-type layers in the same step, and I think IMEC has recently demonstrated some very impressive cell results using this type of process. And so with that sort of background, we sort of wanted to know, well, what are the electrical characteristics? What's the recombination like? What sort of contact resistivities can you get? How is this affected by your surface concentration, your dopant depth? And how do these trends compare with other things like aluminium evaporation? So the first thing we had to do was just develop a process. So nickel plating is essentially, it's quite complex, but in its simplest, it's a redox reaction. And there's two sort of approaches. One is with activation. This is kind of like the old school way of doing things. You use a palladium to activate the surface, and then you get a catalyzing site for the deposition. With activation, you have essentially either a galvanic displacement reaction or a reducing reaction in the case that a hyperphosphite agent is in there, or both. It's not quite clear. But nonetheless, these are the two chemistries, and we tested both in this work. So this is kind of like a diagram of the nickel plating process. Essentially, this here shows the galvanic displacement reaction where electrons are supplied from the silicon itself. Similarly, you can have the reducing reaction to form an oxide at the surface here. The nickel then deposits in the case that you have a hyperphosphite reducing agent, which was, by the way, present in both the palladium activated and non-palladium activated solutions. You then get this autocatalytic growth, and then essentially you have this nice thick layer of nickel at the end, in theory. So we spent a bit of time developing this process. It's a pretty simple setup. We had an immersion heater in water and the plating solution in a bath. It's one of the advantages of nickel plating, electroless nickel plating, sorry, it's quite a simple setup. And we basically did a time series of growth at different intervals. And this is an example of one such imaged interface showing a nice uniform nickel layer deposited onto the polished surface. Let's not do that. And sorry. So this was the results of that initial characterization experiment. And you can see here there was sort of like this very highly non-uniform growth for like the first minute or so, which was followed by a pretty consistent growth in the autocatalytic phase, as you like. So that was our process characterization, and we got a nice fit out of that. This next thing was a boron diffusion process to develop that. So this is sort of just like the results at the end, and it's a pretty messy graph because there's a lot of different profiles which overlap there. But what I was essentially trying to do was have similar surface concentrations for different depths, or different depths for the same surface concentrations. And so I just want to point out, for instance, profiles 1 and 2 have very similar surface concentrations but drastically different depths. Similarly, profiles 3 and 4 have similar depths but drastically different surface concentrations. And similar things can be said for 5 and 7 and 6 and 8. And so this was sort of how you could modulate, say for instance, the effect of surface recombination from just having a high surface concentration versus shielding by having a very large distance between the end of the diffuse region and the metal interface. So how did we extract J0C and the contact resistivity? So the contact resistivity was via circular TLM and and also via linear TLM, so for the different two chemistries respectively. And the contact recombination extraction was a little bit more complicated, involving a method published by Andreas Fell using Quokka. Now, I've listed the steps here, and before I sort of explain them, the general principle is that in Quokka you can simulate a PL measurement. And so if you have an image of your sample which has a metallized region and a non-metallized region, you can essentially measure the PL counts in each of those regions respectively. If you can then characterize the unmetallized region using, for instance, QSSPC, and for instance, get the thickness, the ECV, the sheet res, the reflectivity, the bulk resistivity, the bulk lifetime, etc. You can then simulate that structure in Quokka and essentially take an area where you have in Quokka a metallized and a non-metallized region, and the only thing that you don't know is the J0 of your metallized region, and you can get your PL that you measure from your image to match the PL that Quokka simulates just by having that single free parameter, which is your contact recombination. So that's all in a paper there, and if anyone has any questions, I'm happy to explain that in more detail. But that's essentially the process and the idea behind the process. So this was the fabrication and the test structure. So essentially, double-sided boron diffusion, capped it with aluminium oxide, capped that oxide with nitride, photolithography etching, and then metallization for both plated and evaporated samples. Now, the evaporated samples were evaporated aluminium, and they were used as a reference to compare the performance of the plated nickel relative to the aluminium. And this is the sort of the test structure pattern that we used. So it was a 4-inch wafer. The red is the QSSPC calibration area. So that's, like I said, that unmetallized region that we can measure to characterize the J0 in that area. These are the circular TLM patterns. You can see the linear TLM patterns on the edge here. And these green boxes demarcate just basically arrays of metal dots, which we've patterned. And those dots had different geometries so that you could have different contact fractions. So in total, there were 15 different contact fractions from, I think, 0.05% to 30%. To see if there's an effect or a signal there with different contact fractions versus your contact recombination. So starting first with the contact resistivity, I've got a plot here of all the contact resistivity results from this work and also some comparative literature values. So I'll just start by saying these orange and yellow values are my work. The purple and pink are the other published values of plated nickel contacts onto P+ silicon. There's some Ale evaporated work that I did relative to some published values of Schroeder. These are basically chosen because they're commonly cited. And here is sort of like these simulated curves of the theoretical contact resistivity for a thermionic field emission process. So that's sort of like the theoretical limit of how low you should go. So actually for a nickel-silicon interface, the barrier height is such that in theory, you should be able to get a better contact for nickel-silicon contacts as opposed to aluminium-silicon contacts. But as you can see, I was nowhere even close. But nonetheless, there's a few key things I wanted to point out. So there was really no key trend that I found, at least in my work, for contact resistivity and surface doping concentration. You'd expect things to sort of drop off with increased with increased surface doping concentration. And I think that's simply because I'm so far out of the range that it doesn't really model that ideal process, that I'm not even sensitive to it yet. Generally speaking, the nickel contacts were more resistive than the aluminium contacts. And also that I really struggled with process inconsistencies. So for instance, here you'll find that the lowest electroless nickel results were actually for quite a low surface concentration. But that was not really consistent across the same processing range. And I'll talk about that in more detail, but I think it really highlights some of the difficulties with an electroless process where you don't have control over the potential at the surface to try and manipulate what reactions are going on. So this was, for instance, an image of the interface, and I've sort of said that already, but we think that there's likely an interfacial oxide layer which affects the contact resistivity for the plated samples, and that in some cases you can sinter through that, and that explains the low result anomaly that I pointed to before, and in other cases you can't. And the thing is that that interfacial oxide can be very difficult to control, and it's affected by the initial chemistry at the surface. And it's something we haven't quite been able to study yet, but hopefully something we can put to rest with further characterization of the interface. So we're trying to do more imaging. Hopefully TEM imaging can resolve that interface better. But we also just need to repeat the experiment and do a bit more work. Now turning to contact recombination, you could see here plots of contact fraction versus the J0C that we extracted. And so the plated samples are in the blue and the evaporated samples in the red. And essentially these are 4 different diffusion recipes. So P1, 1, 2, 3, and 4 correspond to the 4 recipes I was talking to before. You can sort of see this one has got the junction depths and the surface concentrations are written there for reference. So in general, we found again that the plated contacts had higher contact recombination than the evaporated contacts. Interestingly, there's a range for each sort of contact fraction of J0C values that you can achieve. So that might suggest that the contact fraction, the contact design, so in other words, for instance, like the perimeter area, so the perimeter to ratio area actually has some effect on the recombination characteristics, possibly due to effects such as current crowding and like the carrier transport to the metal contact area. These things can actually affect your contact recombination. Although there was no real statistically significant trend with contact fraction versus J0C. So there just really weren't enough data points to draw any strong conclusions here. When we look at the same thing for junction depth, as the surface concentration increases, we found that the contact recombination decreases for some plots. So we found that was significant for so this one here and this one here, but really just not enough statistics to prove that, well, to say that with confidence rather, for B and D. Similarly, as junction depth increases, the J0C decreases, so this is that sort of field effect passivation that theory sort of suggests we could see a correlation there. So that was good. So I just wanted to talk a little bit about some of the uncertainties in this method. It's not a straightforward method, essentially, and it relies on you being able to do a lot of things correctly. So there's a lot of sources of variance, for instance, sample non-uniformity. So I've got sort of the PL images of my process wafers here. These are actually all the evaporated samples, and these are the plated samples at the bottom here. And this is the calibration region in the center, you might remember from the schematic I showed earlier. And essentially what I was assuming in the simulation is that this is a just purely passivated surface, there's no non-uniformities, but in reality, and I did this experiment far too many times than I'd like to admit, it's actually very difficult to do this sort of processing and achieve like really perfect surfaces. So I got kind of closer here, but not so much here, and so that affects the J0 that you extract, and then that you then use to simulate the J0 in the metallizer regions. The pixel resolution of the PL camera, so I think the PL camera upstairs has an area, and you guys can probably tell me a bit better in the PL group, but it's roughly like 120 microns, I think, is per pixel, 120 microns per 120 microns. And so if you have feature sizes smaller than that, there's obviously some aggregation of the signal as is detected by the camera. So that may not be able to be resolved in the simulations. Similarly, there's a sensitivity to the bulk lifetime. So you're assuming that your contact recombination and your PL is not affected by your bulk lifetime. And you can see we've done a little simulation here of the bulk lifetime versus your PL counts. And for low bulk lifetimes, there's quite a significant range of PL counts that you can achieve for the same bulk lifetime. Whereas over here, it's relatively flat. So you can see I've plotted here exactly where each sample fits for the J0s that I extracted. And so these ones here have got higher sources of variability because of that dependence on having to have a high bulk lifetime. There's also optical absorption at the rear, so there is some absorption in the metal. We use short pass filtering to try and reduce the amount of signal which gets reflected off the back, but nonetheless this will affect your signal and therefore the amount of PL counts that you're simulating. So that'll essentially make your sample look more recombinative than it actually is. And so some of these reasons can account for some of these differences, but most of it is just in systematic error in this method. But trying to explain why the plated might not be as good as the evaporated, there's likely to be some surface roughening from the etch reactions. So we use a very highly alkaline solution to reduce the pH, to increase the pH of the plating solution to try and get better adhesion and uniformity. However, highly alkaline solutions can etch silicon, although we do know that boron is a good alkaline etch block. So there's some interplay there, and if there is some etching, that's likely to affect your surface recombination. Now, that's not the case for an evaporated contact because it never goes into any alkaline solutions. If there is some diffusion of nickel into the silicon during, for instance, sintering, we might be able to image some lattice distortion in TEM imaging. So that could account for some of the recombination. I already spoke about etching of the silicon surface and also just general surface contamination. So the plating process and patterning is a lot more handling intensive than the evaporated process. And so it's likely also that there's some sort of contamination here, despite my best efforts, which could possibly be affecting the contact recombination. So in summary, we developed an electroless nickel process. We did achieve good results, and for instance, that one which did sinter well, we did achieve a low contact resistivity value. However, it was not as good as the aluminium evaporated samples, and there are issues with process repeatability. We did show that the diffusion profile has an impact on the electrical properties, which I'll list here. And really, we need to do some more interface analysis to ascertain the presence of an interfacial oxide, as it may affect the growth mechanism, the contact resistivity, and also account for the differences in contact recombination. So the third part of this talk is about surface recombination of diffused and inverted/depleted surfaces. So this work came out of an anomaly that we saw in the literature related to this type of symmetrical structure. So back in, I think, 2006, people were starting to explore silicon nitride on PLE+ diffused surfaces. I know Florence Chen was looking at it here. Mark Kerr, I think at ANU, was also looking at it. And so just to remind people, although I think everyone's kind of familiar with it here, when you look at the lifetime of this sort of sample in high injection, you expect a linear trend of the lifetime versus the excess carrier concentration. When people were looking at this type of structure, though, they saw this non-linear trend, and it was really not accounted for until we looked into that. So we were trying to understand, firstly, well, why does it bend like that? Because when it does bend like that, you can't really apply the Kane-Swanson method and extract the J0 because it's really not a linear trend in high injection. So the first thing we did was we took photoconductance and photoluminescence measurements to try and replicate that and show that it's not just some sort of QSS-PC anomaly. And so, sure enough, we got a good agreement between the two curves for a symmetrically diffused boron sample, passivated with silicon nitride. And just as a reference, that was the same sample which I then repassivated with an aluminium oxide. So it sort of indicated that it was something to do with the surface passivation and the electrostatics at the interface. Then we tried to simulate that. So this was work that Fajun Ma helped out with. So essentially what we did was we characterized our sample. We got the ECV profile, the generation rate, and the thickness. We then applied all the relevant and state-of-the-art semiconductor models. And we looked at the SRH recombination at the surface, particularly varying the interface charge, the capture cross-sections, and the defect density. We put all that into a Centaurus simulation, and we simulated a lifetime curve in a very similar way that the lifetime curve is actually measured. And we were able to, long story short, fit simulated and measured lifetime curves. So it was like, okay, that's cool. We can sort of account for this with SRH statistics and taking into account the interface charge at the surface. But to really sort of understand, well, why does it bend, we had to go a little bit deeper and look at what's actually happening at the carrier concentrations at the surface. So understanding the nonlinearity. Basically, it's the result of a change in minority carrier concentration at the surface. So essentially, the sample's transitioning from depletion into inversion conditions. So what we have here is a plot of the carrier concentrations as a function of depth into the sample from the surface. And so here you have, in the dark, and because of the surface charge, you can see there's a significant uptick in electron concentration at the surface. Similarly, there's a significant downtick, if you like, in hole concentration due to the charge. And note that this is really just over like an angstrom or a nanometer. It's a pretty small part of the surface. If you increase your injection level, so that's this range here, you can see that your carrier concentrations start to approach parity. So this is the dot dot dash line for both the red and blue respectively. And as you continue into high injection, you get to this region here where they actually can overtake, and you've gone from depletion into inversion. And so what's happening there is that there's a difference in the recombination rate as a result of the different, capture cross-sections of electrons and holes respectively, affecting your overall recombination rate. So quick summary, we showed that this nonlinear behavior is a result of the surface becoming inverted with increasing injection level, and that we can fit this in Centaurus. The question then was, well, this is kind of a unique bend. Maybe we can start to fit and extract some parameters from these curves. So what we started to do was model actually the carrier concentrations outside of Centaurus. So I developed a statistical model to calculate the surface concentration of carriers, taking into account Fermi-Dirac statistics, surface charge, band bending, band gap narrowing, because it's essentially a heavily doped surface, degeneracy, and just wanted to study the relationship between charge, surface concentration, recombination, and your injection level. So that brings us to point number 4. So what we have here is firstly a plot of surface band bending versus excess carrier density for a given surface doping and for varying fixed charge. So essentially what I'm plotting is this psi s, which is a result of interface charge Qf from a dielectric, or for instance, if you've charged it with corona charge. And so essentially what you can see is that this degree of band bending is a function of your interface charge. And so that was kind of what you'd expect. People have shown that. But then if you take it a step further and look at how this affects your surface carrier concentrations, you can come up with some funky plots on the ratio of holes to electrons. So this is essentially showing, are you in accumulation, depletion, or inversion? So to try and make sense of this, over here you have more holes than electrons. Down here you have more electrons than holes. So we're looking at a p-type surface, which means in this region you're either accumulated or depleted, and in this region you're inverted. And what it shows is that as a function of injection level, how that ratio changes for a given interface charge. So you can see here, if you have lots of negative charge, you can increase your excess carrier density. It's really unlikely that you'll ever get pushed into inversion. Similarly, if you have a strong positive charge, you're heavily inverted and you stay in that range as you increase your injection level. Interestingly though, there's this intermediate case where you can actually go from depletion into inversion as you increase your injection level. And that's sort of what we were showing before. And you can also plot this where you keep the charge constant and show that, well, there's a range, and then think, well, if you have a particular dielectric with certain characteristics, there's a range of doping levels within which you can actually experience a transition from depletion into inversion or be entirely immune to such a change. So what does this have on, for instance, what effect does this have, on the surface recombination rate? You can see that there is essentially, you can have a variable J0 S. And since the J0 S is related to the slope of your excess lifetime, your inverse lifetime curve, that sort of explains that the curvature. So you can actually separate the effective charge and your captured cross-section, so your surface recombination velocity parameters, and show that these two things can actually have different shapes on the overall curve. And so we tried to show that in actual samples. And so this is a sample which got 3 sequential anneals, and we're able to fit that by mainly showing that the DIT has changed. Similarly, we took a sample and we subjected it to corona charging, and we're able to fit it predominantly by changing your fixed charge. And basically what we're able to show is that these two things have different signatures, and so you can separate those two things out separately. And moreover, you can have a certain range within which you're sensitive to that curvature, and therefore you can actually extract your interface charge if you know your doping level. We showed that for also hafnium oxide samples on p-type diffuse surfaces, and also aluminum oxide passivated samples on n-type diffuse surfaces. So here we have, the fitting results of fixed charge and effective SN0 and SP0 values. They're actually quite low compared to what is usually reported, and that's, we think, because we've really only simulated a single mid-trap state, and therefore there's some aggregation there, which means you come out with such a low value. But I'm happy to talk about that in more detail. But for now, I'd like to very quickly talk about how this all applies to diffuse homojunction IBC solar cells. So this was work I did with Mike Pollard and Taz out at Southampton. And basically the impetus was to look at novel light trapping structures on IBC cells. IBC cells being an ideal cell base to test this stuff on because there's no contacts on the front. So my role was really to fabricate the baseline solar cells for these. Now, this is later. this is essentially the fabrication process flow. I won't go into it in too much detail apart from to say that it's a lot of steps and it follows very closely the ANU state-of-the-art IBC that they've recently published, or published I think 2 years ago now actually. So it has diffused N+ and P+ regions, it has evaporated aluminium contacts, and we have silicon nitride passivation on the front and an aluminium oxide silicon nitride stack on the rear. In some instances, we actually use a silicon oxide stack on the rear. So we talked a lot about, in developing this cell, some of the processing issues you can have. I want to highlight 3 key things that we learned, which we recently wrote up in a paper. The first is that you should avoid E-beam evaporation if possible, at least in our experience, because we found that I think this X-ray emission during the E-beam process is actually causing some sort of bombardment on the surface. So on the left you have a wafer which was before and after sintering, which shows the effect of E-beam damage, particularly in this unprocessed region here. Similarly, we swapped all our processing from RIE etching to wet etching because we found that the RIE process itself was introducing damage to our surfaces. So if you look at image B, this was just a raw wafer that we just exposed on the right-hand side through our mask, and this side we just did a wet etch and then repassivated. And you can see there's some residue here of the pattern where the ions got through. And it's even worse actually when you diffuse through these layers. So this half of the wafer was patterned via RIE, this half was patterned with wet etching, and with the exception of these 2 spot contaminations, you can see if you do a boron diffusion through that and passivate, this is really bad. So the last thing was we tried, so recently there's been work on stabilizing the bulk lifetime of float zone wafers. And that essentially involves doing a high temperature oxidation before any processing and then stripping off the wafers. And so this was an example of 2 wafers which we sort of stitched together. The right-hand side had the bulk stabilization process, the left-hand side didn't. And they were then subsequently identically processed. And you can see that the PL prior to metallization was much greater on the bulk stabilized side as opposed to the other. So we wrote about that in a paper recently and sort of quantified that. But here's sort of a nice demonstration of the effect that it had on our lifetime prior to metallization when we implemented each of these sequential improvements. So in terms of where our baseline is now, for a polished IBC cell, we're at 18.3%. It's not amazing, but it's not particularly bad either, considering it's polished and what we're trying to do. I'd like to speak more now about what I was interested in, which is kind of what happens when you try and passivate these dual polarity surfaces. And essentially, I want to talk about what happens during the diffusion process, and that's when you diffuse through a mask. In the same way you get diffusion into the surface, you get like a lateral diffusion because essentially the diffusion gradient doesn't discriminate with depth, it just sees where there's not it and it goes there. And so afterwards, you have this sort of surface depletion region in the similar way that you have a junction into your sample. And so I was interested in the recombination at this particular surface. And to sort of image that, I took that same sort of surface recombination and carrier statistics calculator that I developed before and just sort of looked at how the J0S looks if you vary your doping level from acceptors to donors for varying interface charge. And you can see here there's a peak where you don't have any interface charge, which is in the low dopings, and similarly that peak moves out as you have higher levels of charge for higher dopings, and that's all related to where the carrier concentrations approach parity. So you have your highest surface recombination potential when your minority carrier concentration approaches that of your majority carrier concentration. So this was kind of interesting because it sort of suggests that you can spatially affect where that peak surface recombination occurs if you change your interface charge. So we looked at this with Centaurus, and this is a map of our device, the recombination. Red is higher recombination. The N plus regions are here. This is the N, and this is the P diffused emitter. And this one had a surface charge of -11, so it wasn't quite 0. And you can see that we've been able to actually put the charge in this really big undiffused region here. So we've been able to maximize the recombination in this region here. And so that was sort of like a proof of concept for us with simulation, that we can manipulate where this recombination occurs. So we were then able to sweep basically your interface charge on this y-axis here and your peak surface doping here to sort of see like, well, what's the optimum range for our current geometry and where do we want to be for our, because we put in all our diffusion profiles, all our J0 characteristics of that sort of geometry to try and optimize our device. And what you can see here is that essentially we were better off in a negative charge, which is why we opted for aluminium oxide, and that there's a particular sweet spot if we could hit our doping in this range and get our interface charge high. Interestingly, I took some published value ranges of typical surface recombination velocity parameters and interface charge parameters, which are achieved for state-of-the-art passivation processes. And you can see that this sort of explains why people use amorphous silicon like Kanaka does, for instance, or silicon dioxide like ANU did, because even though you have low interface charge, because you can get such a low surface recombination velocity, you can actually reduce your, actually achieve, good efficiencies. What's interesting though is that this suggests that if you can get high enough negative charge or high enough positive charge and have a good interface, you might be able to achieve similar performance with aluminium oxide and silicon nitride. So that's something we wanted to investigate, but didn't actually get around to doing. However, we were able to sort of forecast the effect of nickel plating onto the solar cells. So what we did here was we looked at, well, what's the effect of the contact resistivity? We did this in Quokka because Centaurus doesn't allow you to simulate the metal silicon contact resistivity like we wanted to. So essentially what I was able to show is that for our current baseline, we aren't really limited by the state-of-the-art nickel-plated contacts. That's the sort of band here. Alternatively, we would sort of be limited to about 24.5% if we really had all our processes firing and everything was working out. So it sort of suggests that for the range of nickel-plated contact resistivities we're able to achieve, we wouldn't be able to realize the full potential of our devices. So it sort of shows that still even more work needs to be done on that process, even if we had it working at our current best. And that's it. So in summary, with IBC cells, careful processing is required to avoid bulk and surface damage, and we want to show eventually that ALOX and silicon nitride may effectively be used to passivate the rear of these high-performance IBC solar cells. The surface recombination modeling helped us develop a novel method of extracting the interface parameters, and we feel that there's significant potential for electrolytic nickel-plated contacts. However, we really need to improve the repeatability and understand the differences between aluminium silicon and nickel silicon interfaces. Sorry, that's a repeat. Future work, so we're still working on the IBC solar cells, that's ongoing, and we're working on the baseline process, and we're going to try this experiment with different rear dielectrics. If I can find the time, I'll try and write up that surface recombination model into a freeware software that people can use to simulate and fit lifetime curves. And with the electrolytic nickel plating, we're actually still doing some characterization to try and understand what's going on. With the ALOX wraparound, it would be really good if we could investigate the cause of this actual improved contact resistivity, as opposed to just simply report what the effect is. With that, I'd really like to acknowledge all the people that have really contributed to this work, in particular supervisors Bram and Alison. Thank you very much. There's been really a lot of collaborators that I've listed here, and in no way is this everyone, that have helped with the work. Of course, ANF, SURF team, LDOT, none of that would be possible without them keeping this stuff alive. And ARENA, of course, for the scholarship funding. And finally, all the wonderful people at SPREE that have made my PhD livable, bearable, enjoyable, and worthwhile. Thank you.
Thank you, Alex. It was great. We're a bit late, so I'm not sure if we have class after us or not. So maybe if you have a question, just find Alex. He's here in the next few months. And let's thank Alex again for a very, very nice talk.